Hello and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mounts, and I'm glad that you've taken the time to join us today as we look at our topic of 5 error-proofing prevention tips, techniques for the assembly process. And if you have any questions, feel free to put those in the chat, and we'll talk about those at the end of the presentation. And error proofing comes from Japanese manufacturing principles of poka-yoke or poka-yoke. You may hear those terms used, but it's basically a way to craft behavior to help from preventing a mistake or an error. And we see this in everyday life that we go about. And if we want to start our car, our foot must be on the brake and the car must be in park or in neutral for the engine to go ahead and start. If we're on an elevator, there are sensors in the door mechanism to make sure that that door doesn't close on something or someone accidentally. And then if we're using a gas pump, the nozzle won't dispense fuel unless it's completely in the car and will shut off when it's filled. And then also, if we're using an outlet or a plug, they're typically set so there's only one way that that plug can go in and be used. And so we see this type of error proofing again throughout our daily lives. And that's some of the things and some of the techniques that we want to go ahead and use in the manufacturing process. And if you've been with us, you know, we highlight manufacturing risks during most every webinar that we have, but you know, no one wants to manufacture defective parts. They don't want to have parts rejected by a customer or returned by a customer, because that just creates more work, wasted time, wasted money in scrap or rework. And especially if it's a safety critical type of application where it could involve some really tragic things or things like, you know, injury and things like that. We don't obviously want that to happen. And so one of the biggest risks that come when we're dealing with any type of assembly process is going to be the human error that may happen within the assembly. And that could be from a lack of training. It could be from a lack of the operator knowing what they're supposed to do or even why they're doing it. They may not necessarily be paying attention to what they're doing, and things get skipped or passed over, or they use the wrong component, and we'll touch on that a little bit as well. In the cause for defects, again, using the wrong part in an assembly, or not fully torquing something correctly, as we're looking at our torque output, fasteners that are skipped that aren't necessarily being fully torqued, or missed or skipped, or fasteners that may be over torqued, again causing problems and leading to a possible failure. So all of these things kind of combined into things that we want to try to avoid. And how can we implement some of those things within the assembly process? So the error proofing principles that overshadow kind of the entire error proofing philosophy are going to, how can we eliminate errors from happening? How can we prevent them from happening or occurring? What equipment or materials or processes do we need to replace in our current application? What things can we automate? So what type of processes can we do to help minimize any type of action that the operator must need to do, where we can combine different steps together? and help to automate that process. If there is an error, we can detect what that error is, and again, helping us to minimize those errors. And in relation to the detection that once an error is detected, we can go ahead and we can fix it right there before it goes any further. So those are kind of the again the overlying error proofing principles. Now, when it comes to fastening, the five error proofing fastening techniques are the first one is going to be that we ensure torque control. Now, we use torque to help generate clamp force in a fastener, and well, actually, we use the torque to create tension in the fastener, which creates clamp force on the application. So as the two parts come together, the tension that's in the fastener is what's holding those components together. If we don't have the proper torque, then that can be an issue and we could see failure. If there is an under-torqued situation, then we don't have enough tension on the fastener and the parts could eventually begin to move and we could see failure that way. Conversely, if we have an over-torque situation, then we have a lot of tension on that fastener. Any type of shock or vibration there can cause that fastener to break if we've moved that fastener past its yield point and into the plastic region of that fastener. And so ensuring that we have the correct torque control is going to be the first error proofing type of setup that we want to have for that particular principle. So number one, ensure torque control. Our second key is going to be to implement process control. And so the process control allows us to be able to combine different processes or different activities and have it go into a one type of operation so that we can help to control how the process moves forward. And if we can do that successfully, then we have a little bit more control over how the operator can interact with the application or with the part that's being used, and that we can help to automate some of those processes within the fastening process. And we'll look at these different scenarios during our demonstration portion of today. But process control can really help give us a lot of control over things that the operator doesn't necessarily have to do to move from one step to another. So that is key number two. Key number three is going to be screw counting. And obviously this makes sense. We want to make sure that all of the fasteners within a particular operation are accounted for. And that can be within a subset of an assembly and then the overall assembly as well, all tied into what was key number two, part of the process control. So if we can help again to make sure that all the fasteners get torqued, they're torqued correctly, that can certainly help with our error proofing process as well. Number four is going to be job management or job managing. In the event that you may have a scenario where you have different parts that are coming through a certain area for building, and you want to have different jobs set up or different models set up for a particular application where you may have 2 or 3 or more preset changes from one setup to another setup. You might want to have that type of a high mix, low volume type of scenario, or just different mixes as they come through. You want to be able to I said that twice. That's really important. So you want to make sure that you have the ability to adjust the job for the part that's coming in. And that can all be part of the process control as well. but having that ability to adjust without having the operator do anything, but be able to move from one job to another, again, can help in minimizing the errors that can take place in that particular assembly. And then finally, our last point is being able to have real-time monitoring of what's happening during the assembly. And this is crucial to be able to alert the operator if there is an error, what that error is, and then give them the opportunity to adjust or fix that error so they can move on through the rest of the assembly, which would go towards the screw counting, which is part of the process control. So kind of all five of these work in concert together. And another benefit of the real-time monitoring is to be able to gather fastening data as well that you can either have exported to an MES system, or you want to be able to follow the results of a particular build or a particular part, or maybe you want to monitor how different operators function with their throughput or different shifts. All those types of data collection type of analytics you can get from the unit itself, which is going to allow you again to make data-based decisions on your process, which was process or key number 2 in our thing. So those are the 5 keys to the error-proofing fastening techniques. And so that's all well and good, but let's see how we can do this in action. But before we do that, let's go to our poll question. And today's poll question is, do you currently use any error-proofing tools in your assembly process? So I'll give us just a few minutes here to go ahead and answer that. And I'll grab a drink of water. All right. Well, I'm not sure if there is an issue with the poll. Oh, there we go. All right, perfect. So the majority of the respondents is yes at about 80%, and obviously the remainder no with that poll question. So thank you very much for participating in that. And so in our demonstration today, we're going to be highlighting our EC DC control tool. And we have this currently connected to one of our torque arms and the tool here. And this is the display for the controller. And what you'll see on here is basically giving us our information on what our last torque value was. We have which preset we're using right here. It's going to show us what our preset target is, our RPM speed. And then down below we have the time of our last rundown, in milliseconds. And then our angle or the amount of turn that happened in our last rundown. We have our screw count function here, and then there is another feature over here, which is our snug angle, but that's for a different discussion. But nevertheless, let's go ahead and look at how we can implement the 5 principles within the use of this particular tool. And so let's go ahead and move forward. So I have a thread block here that we'll use as well to go ahead and do our different scenarios with our a tool. And so the first thing we want to do is obviously we want to ensure our torque control. And so there are a couple of settings and items that we can use within the tool that will allow us to help do that. Now, if we want to go in and change our torque value, we can do that in our parameter menu, which gives us the ability to go into our fastening tab. And from this point here, we've got a couple pages of menus that we can use to help set our torque value and again ensure our torque control. So the first thing we can do is look at our target torque. So right now it's set to 2.55 inch-pounds. If I want to change this to, let's see, 2.75 inch-pounds, we can do that. And this has now updated preset number 1 to 2.75. And so at this point, we need to then go ahead and after we've programmed our preset torque, we can go ahead and then set what would be our tolerance to make sure that we're going to be hitting this number correctly. And that's going to be right here with our torque limit percent right underneath there. Now, by default, these come set to 10%. So any reading outside of 10% of our torque value, the unit is going to display an error. If you want to change this value, you can change it to whatever your percent limit is going to be for that to make sure that you're within your particular torque limit percent. Now, some of the things that can cause this to be outside of it, if we tighten up this tolerance, could be things like RPM speed. It could be if there are washers that aren't with part of the assembly that aren't being used and things like that, that would alert us that the torque limit percent is out of its tolerance. And so if we come back out, we can come all the way back out to our preset. Right now, you can see we're still at preset 1, set at 2.75. I can go ahead and run this fastener down. And we get our torque value, and that's within, well within the percent limit that we have there. But this gives us that ability, or to make sure that we've achieved this number. The other thing that is on this tool to help ensure that we have the correct torque value is going to be a transducerized tool or a current control version tool. The transducerized tool does have a sensor built into it, so it's constantly monitoring what the torque output is. If we're using a DC tool that is a current control product, it's basically referencing the amount of current draw to a specific torque value that is being implemented there. So with a transducerized tool, we're monitoring and getting that real-time information from the tool on the output that was generated. So again, ensuring that we have the correct torque control. So now, what is the next thing that we can add to this to make sure that we're achieving our torque control? And that is, we can go ahead and enter in an angle tolerance as well. So if we come back into our menu and we go to our fastening, we have the ability to monitor the amount of turn or angle that happens for that fastening. Now, these fasteners that I have on the thread block, they are lifted to about 1800 degrees of rotation, just so we can highlight this. And if you have a scenario where you are experiencing any type of cross thread issues, or the operator may not necessarily detect when a cross thread happens because they're not paying attention, the tool will torque at whatever value the tool is set to. When it reaches torque, it's going to shut off. Even though the fastener did bind up and it's not fully seated and you have zero clamp load for that. But we can come in here and we can set what would be our minimum angle amount. And so we're telling the system to judge when the torque is achieved that we've met a certain amount of turn to be able to count that as a good fastening. And so in this case, if we set the minimum angle to, let's say, 1,000 degrees of rotation, we must meet 1,000 degrees before the application, or before we hit torque, to make sure that that is going to be a good rundown. And so in this scenario, if I come back out, we're on our fastener, and I'll just use, let's say, this fastener over here, which is already primarily torqued. But if we just run that down, and you can see we get an error notifying us that our minimum angle was not reached, and we only went 635 degrees of rotation. We didn't meet the minimum amount for that particular one. So if we had a cross-thread event, this would alert us to make sure that we come back and we fix that that fastening. Now we can also help to ensure the torque control by adding another angle requirement, and that would be the maximum amount of angle. And so if we had a strip fastener in our application, the driver would continue to turn, and we wouldn't necessarily have any torque achieved, but we can set our maximum angle, and let's say we want to set it at 2,400 degrees of rotation. If we then come back out and we go to our preset, and I simply just run the tool, once we get to 2,400 degrees of rotation, we get an error stating that our angle is over. And so basically what we've done now is we've error proofed that fastener based off of the torque value, based off of the minimum amount of turn that must happen, and then based off the maximum amount of turn that could happen, basically to help us, again, ensure that we have the correct torque achieved, which we're trying to get the correct clamp force for that. Now, if we want to make sure that the operator continues the operation all the way through without stopping or letting go of the trigger, we can do that as well. And that would be through the use of our what would be our fasten stop alert. We come back into our parameter section, and in our controller, one of our settings in here is going to be our fasten stop error, which is right here. So if I turn this on, what will happen now is if the operator comes in and tries to do an operation, especially if we're monitoring the amount of angle that happens, comes in and we let go. Sorry. We let go of the trigger before the operation reaches torque, then we would get what we just saw there, our no torque complete error message. And we kind of were in between our fastening, our minimum and our maximum angle here at 1,900 degrees of rotation. So that error occurred. If I go ahead and let go early, no torque complete. Yeah, there we go. So again, this is one way that we can help the operator make sure that they've completed that particular fastener by making sure that they've run that completely down to the correct amount of torque, again, ensuring that we have torque control. Now, when it comes to process control, what we can do is go ahead and if we have an assembly, let's say we've got a series of fasteners that will have different torque values that we need to go ahead and move through the different fasteners at different torque values. And as I mentioned before, the part about job managing is we can go ahead and create a job function that would allow us to be able to set the number of fasteners that we're going to use for each preset within the assembly. And so just to make this easy, in our parameter section, we have our model mode, which again allows us to be able to set different operations to allow us to move through the process without the operator having to change or connect with the display to change a certain preset. And models are one way that we can do that. We can also do it through the use of an input device. It could be a barcode scanner, it could be direct I/O connections through a PLC. But models are one way that we can do that. And so a model, basically we have 15 different models that are available for us to use. And those 15 models can be comprised of the 15 different presets that are available to be used, and different actions within that as well. But we'll do a simple one here. And so what you can see is up here we've got a fastening task that we could do first. We'll use preset 1. And we'll just do a count of 1 here just to make this a little bit easy. Our next step is going to be a fastening step on preset 2. And we'll set this to a count of 2. And then finally, we'll do our third will be a fastening step on preset 3. And we'll do a count of 2 there as well. And so if we wanted to do another step within here, we have that ability to come in and we could enter in a fastening step, another fastening step. We could add in a delay. We could wait for an input signal to come in from, say, it could be a pneumatic lock mechanism. And we're waiting for a signal for that to happen before we moved on to the next step. We can also send a signal out saying that we're ready to do a particular item, or we can do a barcode scan to help identify a particular part within that model to track it for review purposes. But those are some of the things that we can do within the model function under the process control type of scenario. And so we'll go in here, we'll go to our controller tab, and we're going to tell the system to switch to our model mode. And so now when we come back out, we have model 1, which is on preset 1, and our step here is fastening, and our count function is now enabled. So it will count that that fastener only if we get a good rundown. So if I go ahead and I run the tool and we go with an error, it does not count that as part of the scenario, and it does not index to the next step within the model. So if I go ahead and then run this down, okay, we got a good result from that fastening. It has now moved to step 2 in the fastening, and that is preset 2. So now we've had a torque change, we've had an RPM change with that, and so we can then now also have our count of 2 that we would be running within this scenario. So I could go ahead and run those down, and now it has indexed and counted that fastener. And now we've got that as a good fastening, and we've indexed to now step 3, which is again a fastening on preset 3, again in model 1. And we can run that down. And then we get a good rundown there. And our model is now complete. So this allows us to be able to utilize the different presets that we can set the tool at within our application. And the operator can simply move through the operations without having to go in, touch the screen, the display to change a preset. And again, or maybe you don't want the operator to have any control over changing the preset on the screen. This is one way that we can do that to allow the operator to just move through the operation, again, controlling some of the automation features that will allow us to do that. So, and that is with the process control. So programming multiple presets is basically what we have just done. That will allow us to be able to do that with our process control. And then we have our real-time monitoring function as well. So all of this information that we see on the screen gets exported or stored locally on the controller for later review. So we get the amount of torque that was applied. We get the torque value that was achieved. We get the amount of speed that was used. We get the actual angle that was done, the amount of time in milliseconds it took. If there was an error, that error would come through and we would get a classification of what that error was. And everything is time date stamped, and it comes via either, again, you can export that through the RS-232 port on the controller, or there's an Ethernet port on here as well, or it can be stored, again, locally on an SD card on the controller. And the big feature, of course, is letting us know that we have an error and letting us go ahead and fix that error in real time before that gets further down the line. And we're ensuring that our process control is correct with our counting function and ensuring that our torque is correct as well. So that kind of all ties in together with our 5 keys of error proofing for the fastening process. So with that, let's going to move us to our question and answers. Again, if you have any questions, feel free to put those into the chat. And let's see, Chris, do we have any questions?
Hello, Dave. First question we had was, what's the difference between a transducerized and non-transducerized tool?
So the difference basically is that the transducerized tool has a sensor that is built into it that allows us to be able to monitor and capture the torque in real time and giving us the actual values that the tool is producing. A non-transducerized tool or a current control tool is basically converting the amount of current that is drawn to a specific output or torque output. And so the difference is one is measuring and one is basically converting. So.
All right. The next question was, can the system be programmed for thread tapping applications?
Yes, it certainly can be used for a thread tapping type of application. We can utilize our angle use in the scenarios that we did through our demonstration. We were looking at torque control with angle monitoring, but we can also tell the system to run to a specific amount of turn or an angle control type of scenario. And that can be used again for a tapping application where we're running down to a specific angle. And then we also have a feature that will allow the fastener, or excuse me, in this case, the tapping element to automatically reverse up and out of that. So yes, it can be used as a thread tapping type of application.
All right. And it looks like that's all we had for today, Dave.
All right. Thank you very much for joining us today. We look forward to seeing you again next month in our webinar. Thank you again and have a great day.